Hey guys, we are starting a new chapter. So, this is chapter 11, sequences and series, among other things. Sequences, probability, and counting theory. Anyway, so this first part is mostly going to be review from Algebra 2, sequences and series. Maybe a little more complicated than what we did in Algebra 2, but it's sort of the same idea. And then as the chapter progresses, we'll move on to other things. So, yeah, so this part's mostly review. But anyway, moving on. So if we remember from back in Algebra 2, a sequence is a string of numbers just going to follow a pattern, right? So we're going to be able to figure out what that pattern is, and we're going to write formulas for that. We have two types of formulas, explicit and recursive. We start talking about explicit formulas. So if I have a sequence, like it's giving me this sequence, 2, 4, 8, 16, 32, hopefully we realize that this is doubling each time. What else is it doing? These are all powers of 2, right? This is 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. So our explicit formula would be that that each term, if the term number is n, this is 2 to the n. So the first term is 2 to the first. The second term is 2 to the second. So these two numbers are going to match. And this is how we can rewrite that to kind of figure that out, right? We can rewrite it and see, okay, what's changing? That's going to be where my n is going to go, the thing that's changing. If this had been 0, right, then we could have put n minus 1 here, because this is the first term, but this is, if this went 0, 1, 2, 3, like that, then we could have put n minus 1. So it may not be just n, but the thing that's changing is the thing that's going to have the n in it. All right, so that's the basics of an explicit formula. And then using an explicit formula, we can find any term. So we could find the billionth term, right? It'd be some ridiculously huge number, but we could find that, right? We can also graph this like a scatter plot. So you can see, oh, that's exponential. So you can see kind of what this looks like. We can also find an explicit formula from a graph. So if we have a graph, we know what the points are. It's exactly the same thing as just being given that sequence, right? Could just write this out as, okay, that if these are going up by 1 each time, then I know that my sequence is just 2, 4, 8, 16, 32. So I can read the sequence off of a graph as well. Okay. So this is just talking about the difference between finite and infinite. So a finite obviously is going to have a specific number of terms. So maybe n is defined, and it's going to stop at some point. And then if it doesn't stop, which most of the series sequences that we deal with are infinite and doesn't stop, it just keeps going. And we don't know what the last term is. There is no last term. That would be an infinite sequence. And most explicit formulas, or well, an explicit formula is describing an infinite sequence. If we would have to state separately from the formula, by the way, n only goes to this specific number. Okay. So, so if we want to talk about finding unexplicit formula. Oh, no, this, sorry, I'm getting ahead of myself. This is talking about how we, if we're given an explicit formula and we want to find the first, in this case, 5 terms of the sequence, we're just plugging in numbers, right? To find the first term, you just plug in 1 for n. To find the second term, you plug in 2 for n, and so on. So you're just plugging in numbers here, and you get out your terms pretty straightforward. Again, you can graph it. It's just a scatter plot where this is the term number, right? And then this is the term that you got. Okay. They can be more complicated, but you're still just plugging in the term number. So the first term, you're still just plugging in 1 for n. Even though there are 3 n's, you're just plugging 1 in all of those places. If you're looking for the second term, you're just plugging in 2 in all of those places. 3, 4, and so on. So you're still just plugging in the number, the term number for n. You just have more of them. Okay. And this one has a slightly more interesting looking graph. We can have piecewise defined explicit formulas. So you can have a situation where you're saying, okay, under this circumstance, in this case, not being divisible by 3, it's going to be, you're going to use this formula, and then if n is divisible by 3, you're going to use this formula. So if you wanted to find the first term, you would use this formula because 1 is not divisible by 3. For the second term, you use this formula because 2 is not divisible by 3. For the third term, you're going to use this formula because 3 is divisible by 3. And then you go back to this formula for 4 and 5, and then this formula again for 6 because 6 is divisible by 3. So you can have a piecewise defined function where you have different criteria. So you're going to use different formulas depending on certain criteria. So that's an option. All right, so now what happens if we're given, so we talked about this kind of at the beginning, if we're given a string of numbers, we need to find the explicit formula. So what we can do here is we're looking for a pattern, right? We're always looking for a pattern. Here we see that we're alternating between positive and negative. So when we alternate between positive and negative, we can do this trick where we do -1 to the n, or n minus 1, depending on which terms we need to be positive and which terms we need to be negative, because -1 to an odd number, right, is going to be negative, but -1 to an even number is going to be positive. -1 to an even number is going to be positive. So to get something to switch between negative and positive, we can just put -1 to the n in front, and then the first term will be negative, the second term will be positive, third will be negative, fourth will be positive, and so on, because the power is going to switch between even and odd. So the whole thing is going to switch between being positive and negative. So that's a trick for that. And then you're just looking for, okay, what's the pattern for the top? Well, it's just going up by 1. It's starting at 2 and going up by 1, right? So I can just call that n plus 1, right? This is 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1. So I can just call that n plus 1. And then here, we're going up by 2 each time. We're up by 2 each time. So I can say, okay, well, this is I can figure out my can figure out my formula for that. The easiest way I can think of to do it, there is a formula for explicit formulas for an arithmetic sequence, which is what this is. But to me, it makes the most sense to say, okay, well, if this is the first term, what would be the 0 term? If it's going up by 2 each time, I can just subtract 2. What's my 0 term? My 0 term is 9. So that would be my y-intercept, because this is essentially linear, right? If I'm going up by the same number each time, I can think of this as being linear. So my y-intercept for just the denominators here is all we're talking about. My y-intercept would be 9, right? Because this is my 1 term. So if I go backwards 2, my y-intercept would be 9. And I'm going up by 2 each time. So my linear equation would be 2n plus 9, which is what you would get if you use that explicit formula that we learned back in Algebra 2. But to me, this makes more sense to think of it that way. What would it be if I went back to the 0 term? That's my y-intercept. My y equals mx plus b. That's going to be my b. I'm going up by 2 each time. That's my slope. So this is my explicit formula. So put all those 3 pieces together. Remember, this piece comes from the fact that we're alternating positive and negative. This piece is my linear formula for the numerator, and then this is my linear formula for the denominator. Okay, so let's look at B. So with B, they're all negative, so we just put a negative in front. We don't have to do this. We can just put a negative in front. The numerator is always 2, so we can just put a 2. We don't have to come up with a formula for that. It's just staying the same. And then in the denominator, hopefully we can recognize that these are powers of 5. These are powers of 5. And if we write them as powers of 5, we can see that it's going up by 1 each time. But it's they're not n, right? N would be 1 here, n would be 2 here, and it would be 3 here. So they're actually n plus 1. They're n plus 1. And you could think of that as a linear formula as well. If it gets more complicated than that, you can think of it as a linear formula and say, okay, what would I'm going up by 1 each time. So my slope is 1. My y-intercept would be 1, because I have to go backwards 1 term, right? So that'd be n plus 1. So if that way of thinking helps you, then you can use that. So it's just n plus 1. What I would do is I would think about what n would, right? N, where your n is always going to go where whatever is changing is, right? So the thing that's changing here are the powers. So your n is going to be in the power. But think about what n actually is, right? It's 1, it's 2, it's 3, it's 4. And then how does that relate to the number that's changing? So it's going to be n plus 1 in this case. So this would be the formula, the explicit formula for the second one. C is pretty easy because it's already in a form where you can clearly see what's changing. So here n would be 1, so that's 1 plus 3. This is 2 plus 3, 3 plus 3, 4 plus 3. So this is e to the n plus 3, and that would be our formula. All right, so this video is kind of already getting long, so I'm going to talk about recursive formulas in the next video. So hopefully this helps. Let me know if you have any questions, and I will see you in the next video.